So we're going to talk about bioenergetics now. Bioenergetics. We got a little bit of things to talk about. So we talked about a few things earlier. We talked about when delta G was negative, positive, and zero. What was the word we used for when delta G is negative? And when delta G is positive? And delta G is 0? And which of these reactions happen on their own without the aid of any outside input of energy? Exergonic. But the endergonic ones are going to need energy input, some way, shape, or form, to happen. We'll talk about that in a little bit. But if the system has achieved equilibrium, that's the point where delta G has now reached its minimum value. And therefore, where G has reached its minimum value. That's why the delta G is 0 at that point. It's not going to change anymore once it reaches its minimum. Cool. We introduce something else in this section, or we reintroduce it. What's that little circle mean? Standard conditions. Delta G naught, standard conditions. What are those standard conditions? Actually, it's not. We'll come back to that. It's 1 atmosphere pressure. It actually doesn't specify a temperature, believe it or not. I can talk about standard conditions at 298 Kelvin. I can talk about standard conditions at 310 Kelvin. I can talk about standard conditions at 5,000 Kelvin. So typically, we actually have to specify a temperature beyond just saying standard conditions. But what it does mean, and this is the most important part of it, is that you have equal concentrations of all reactants and products. And it's not just that they're equal, they're all 1 molar, all of them. All reactants, all products, 1 molar, as long as they're aqueous. If they were gases, and we're not going to deal with that too much here, they'd be 1 atmosphere partial pressures. But all aqueous reactants and products, 1 molar. So you have equal amounts of reactants and products for these conditions to apply. How often do you suppose that happens in the laboratory? Do you ever start with products, usually, in anything you guys have done? Not usually. How often do you suppose this happens in the cell? Actually, every once in a blue moon. Every once in a blue moon, but not very often. So we're not usually under standard conditions. But these are the only values you can look up in a book. But it turns out this works out great for Gen Chem, P Chem, O Chem, not Biochem. Not so much. Because if everything's 1 molar, that would mean your hydronium ion concentration is also 1 molar, which corresponds to a pH of 0. How many organisms have a pH of 0 somewhere in them? How about 0? So you got some couple extremophiles, but I don't think they can make it down to pH 0. So in this case, this doesn't work for us in biochemistry. So we define something new. We put a little prime there. And that prime means not just our original standard conditions we used for regular chemistry stuff, but our biochemical standard conditions, which is a much better reflection of what living systems deal with. And so instead of having an H plus concentration of 1 molar, we use an H plus concentration of 10 to the negative 7 molar. And that corresponds to a pH of what? 7. And notice what's pH in a standard living organism? Usually somewhere around 7.4-ish or something, give or take, depending on the organism. And so this is a much better approximation, a much better reflection of what we're likely to encounter in a biochemical cell. And so we don't usually just use delta G naughts, but delta G naught prime now. And it just implies this. Technically, it also implies O2 and CO2 concentrations that are not 1 molar, but don't worry about those. This is the big thing to worry about. So where do you get that delta G naught prime value from? Where do you get these from? And when I say you, I mean actually you guys. Where would you get them? You wouldn't go in a lab and actually do the experiment and measure it, right? Maybe you would. But I doubt it. Where would you get them? I'd look them up in a textbook, right? Or some big fat chemical handbook. But I'd look them up in a textbook. Sweet. It's where you get them. They're in a book. They're published. Somebody's already figured it out for us. The standard values. Great. So if I looked up a standard value, and then I went for a run, and I came back, and I looked it up again in the same book, should I expect that to change? No, it's the book. It's the number in the book. Now, these don't have standards. These are not the numbers in the book. So how do these relate to the standard value? So what if I'm doing my reaction under conditions that are not the standard conditions, which is really likely? Does this number apply? No, it doesn't. But it's where I start for calculating what the delta G is going to be under my conditions. So, and the way you equate those is that delta G under any non-standard conditions is equal to delta G standard plus RT ln Q. What's Q? Reaction quotient, products over reactants. That's what it is. And so that's where you can take into account the fact that if any species are not 1 molar, that's where it shows up, right there. So again, products over reactants. In this case, one thing to note, so the delta G standard value, where do you get this from? A book. But this value, this is one for the actual conditions in your reaction. So notice, if I looked up, for a set reaction, I looked up delta G standard in a book, and it said negative 30 kilojoules. And then I decided to actually do that reaction. And I started it out under exactly standard conditions. Well, then great, yeah, delta G at that point would be the standard value, and it'd be negative 30 kilojoules, right? But let's say then, I let the reaction go for a while, and it reached equilibrium. When it reaches equilibrium, does the number in the book change? No, that's from the book. It's the non-standard number that changes. That's the number that goes to equilibrium. At equilibrium, that's 0. Not that one. That one, I mean, if for some reaction, maybe some random exception reaction, it might come to 0. But does it have to be 0? No, it's whatever it is in the book. You looked it up. It's this value that goes to 0 when you reach equilibrium. So keep that in mind. So how do I make a non-spontaneous reaction happen in the cell? Well, there's 2 ways. The question is, 1, is it non-spontaneous under standard conditions or non-standard conditions? What if it's not spontaneous under standard conditions? The standard value, if it's not spontaneous under standard conditions, what kind of value would I expect here? Positive. Well, then maybe I don't do the reaction in the cell under standard conditions. Maybe in the cell, I get really non-standard conditions. I get a boatload of reactants and a whole lot of, a whole little tiny bit of products present. Lots of reactants, not very many products. And Le Chatelet taught us that, that's a case where you might shift the equilibrium to the right. So if you're in a state where you have more reactants than you should and less products than you should to be at equilibrium. And so maybe the cell doesn't take standard conditions where I have 1 molar of everything, reactants and products. It says I have a boatload of reactants and only un poquito amount of products. So, and that way the cell manipulates its conditions to make what normally under standard conditions would be not spontaneous to make it spontaneous under non-standard conditions. That's one way to get around it. Well, if it's not spontaneous under standard, let's not use those conditions. Let's use some non-standard conditions. Here's the other way to get around it. What if even under the conditions of the cell, the reaction still, even this value is positive? How do I get around that? I couple it to something else. So maybe a reaction is not spontaneous, but I tie that reaction to another reaction that is. So maybe under the conditions of the cell, this reaction comes out to positive 10 kilojoules. Well, what I need to do is that I need to marry that reaction to another reaction that's delta G value is more negative than negative 10. So maybe I marry it to ATP hydrolysis, and the delta G of that's negative 30-ish kilojoules. And so positive 10 kilojoules for one of the reactions, negative 30 kilojoules for the other, and by the time you marry them, what's the overall delta G for that coupled process? Negative 20, and it's spontaneous. And that's how we might make some non-spontaneous reaction happen. Like if you notice, we talked before about phosphorylation of some, when we phosphorylate an enzyme. When I phosphorylate that, that usually has a big fat positive delta G. So how do I make that happen? Well, most of those kinases use what up as they go? They use up ATP. Because ATP hydrolysis, turning ATP into, say, ADP, big fat negative delta G. And so even though the phosphorylation part of things is a positive delta G, the ATP hydrolysis that's coupled to it more than makes up for it. It's a beautiful thing. All right. We're on this page now. One other thing. So let's say we have had a reaction that's reached equilibrium. What's this value? 0. What's this value? Whatever the book says. Awesome. What is Q at equilibrium, though? It's the equilibrium constant K. And so if we look at the special case of equilibrium, we can find that your standard value is related against your equilibrium constant. I had this up there a little bit earlier. So we'll call this KEQ or KC or something along those lines, but just the equilibrium constant for the reaction. And so the number, it's interesting that the number you can look up in a book, though, is the one that's related to the equilibrium constant. So you can look it up in the book and be like, does it favor the products? And it turns out, if this is a big, fat, negative number, then yeah, that's going to favor the products. And your equilibrium constant's a big number, bigger than 1. But if, this number is positive when you look it up in the book, that's a reaction that doesn't favor product formation. And it actually favors the reactants, and your equilibrium constant's going to be smaller than 1 in that case. But what's nice is I can just look up this number in the book and find out what's favored at equilibrium in a certain reaction. And it's just related through this equation. Now, one thing you need to know, guys, because you may use either or both of these equations in a calculation. What's R? This is the most common value given to you guys for something like this. 8.314 joules per mole Kelvin. What do we usually give you delta G's in units of? Kilojoules. If you're going to do either one of these calculations, you either better make everything joules or everything kilojoules, and I don't really care which, but you better convert. Either the delta G's need to show up in joules, that way he, being in joules, is okay, or convert him to kilojoules by dividing by 1,000, that way everything's in kilojoules. But either way, the units have to match all the way across, or you're going to be adding apples and oranges, and that doesn't work. I want to know what delta G for this reaction is. Glucose plus ATP. ATP gets hydrolyzed, forms ATP, and the glucose becomes glucose 6-phosphate. The glucose got phosphorylated here. I want to know what the delta G is for that. Now, notice, I can't just expect you to be like, oh yeah, I memorized that one when I was like 3, Chad, thanks. So notice I provided you a table of values for the delta G processes here listed. Now notice, if you look at ATP turning into ADP, so technically it's ATP plus water gives ADP plus inorganic phosphate. So for that half of the process, what's delta G, according to the table given to you? So on the other hand, if you look, your table doesn't show glucose turning into glucose 6-phosphate. It shows glucose 6-phosphate turning into glucose. What's the delta G listed for when glucose 6-phosphate turns into glucose? So negative 12.5. Then what would the delta G for glucose turning into glucose 6-phosphate be? Positive 12.5. Just backwards of what's on the table, so opposite sign. Then what is the overall delta G for this process as it's written? Sweet. So if one of them's backward from the provided data, cool, change the sign. Just add them together when you're done. If this were a coupled process, would it be spontaneous under standard conditions? Yes, indeed. Big fat negative number. What do you eat? What is it you guys eat? Food. Define food. If I went out in the parking lot and started chewing on some asphalt, is that food? My body doesn't think so. Doesn't bind to my lips very favorably, I'll tell you that. Very high km value. So here's the deal, your food. How do they tell you how many calories are in your food? What do? They burn it. When they burn your food, what does it turn into? Carbon dioxide and water, largely. A few other little trace things. Notice, you guys also learned about burning something else back in Gen Chem, and it turns into carbon dioxide and water. What did you learn about burning? Hydrocarbons. What's in a hydrocarbon? What elements? Hydrogen and carbon. Sweet. Most of your organic stuff, notice if you eat something, odds are you ate something that used to be alive. Notice not true anymore, right? Because we can make food in the lab. It's great. So anybody make banana oil in OChem lab? You could eat that. I wouldn't recommend it, but you can. So maybe some aspirin, good times. I wouldn't use that either, by the way. So here's the deal. Your food, organic molecules are typically based on hydrocarbons. And when you burn hydrocarbons, you form CO2 and water. Getting how much heat is released when you burn it is exactly what you're doing. Because what do you guys use? What are your waste products? What do you exhale? Carbon dioxide. What do you get rid of in other ways? Water. Sweet. You guys are burning your food. That's why all they have to do is burn it to get delta H. Delta H is the same function. It doesn't matter how you get there. I don't care if you light a match to it or you have a boatload of chemical enzymatic reactions in sequence. If the initial reactants are food and the final products are CO2 and water, awesome. Delta H is the same. That's how they get the caloric intake of your food. They burn it. That's what you're doing in your body. You're combusting your food. You do it slowly in a big sequence of of enzymatic reactions. But this burning of food, this breakdown of food, that is called catabolism. So catabolism. So what's the most common fuel we're going to talk about? So what's that? So probably seen in your other biology classes, we talk about glycolysis and TCA cycle and electron transport chain and glucose. And if you look at the catabolism of glucose, C6H12O6, and eventually we're going to turn it into carbon dioxide and water. In this case, what else do I need to bring into my body to react with that glucose to burn it? Oxygen. That's why you breathe oxygen. Your food needs it to be able to be burnt. And so in this case, if you balance this out a little bit, we need 6 of those, we need 6 of those. In this case, 12, 18, there's already 6 there, we'll need 6 of those. Delta H for this reaction and delta G, both are big fat negative numbers. This is a really spontaneous reaction. It releases a boatload of energy. That's why we eat it. You don't eat stuff that can't give you any energy, like asphalt. Maybe it can, but it can't give me energy. So in this case, so this produces energy. Highly exergonic reactions. It's also an oxidation. So your catabolism process, the breakdown of food, glucose here being a notable example, they're typically oxidations and they release a boatload of energy. Cool, we can look at the other side of things. So if I decided that I wanted to be in a grumpy mood and have big muscles and a very high-pitched voice, what might I start taking? Steroids, and what's the word we often hear right before steroids? Anabolic steroids. Sweet, anabolism is not breaking down, it's building up biomolecules. And so for anabolism, these are typically the exact opposite of catabolism. In fact, photosynthesis is a form of anabolism. What does a plant breathe, if you call it breathing anyways? CO2, and it mixes that CO2 with water, and it uses the energy of light to form glucose, for example. That's anabolism. It's going the opposite way. Would that be a favorable energetic process? No, that's why it needs light's energy to do it. And so for catabolism, it typically produces energy. Anabolism, these require energy. Cool, you're building up biomolecules rather than tearing them down. And so if metabolizing your food is oxidation, then building stuff up, going the opposite way, is typically going to be reduction. And so this whole idea of metabolizing your food and building biomolecules is all tied into redox reactions really heavily. So, and that influences why we have a couple of major cofactors, so like the ones you see on your sheet there. So for catabolism, catabolism heavily involves turning NAD plus into NADH as part of the process. As your food gets oxidized, NAD plus, the cofactor, it's an enzyme cofactor, gets reduced. Typically a big part of catabolism. Vice versa for anabolism, the cofactor of choice is often NADPH. These are not balanced reactions, by the way. So I should show the electrons. These are 2 electron processes. So, but for anabolism, as your substrates get reduced, something else needs to get oxidized. And it's the NADPH that gets oxidized going the other way. So notice in organic chemistry, you might remember, oxidation can be looked at as making more bonds to like oxygen or other electronegative elements, or getting rid of hydrogens. So whereas reduction, the exact opposite. So notice here, catabolism is oxidation, so I need something to get reduced. And in this case, you really should look at the whole process, but it's gaining H's in the formula anyways, and I can see that's a reduction. Whereas here, what's happening to my H's? I'm losing them. Technically, there should be H plus over here on the product side, and there should be H plus over here on the reactant side, but I'm not going to show it. Just want a basic, generic reduction and oxidation. These are some of the big redox cofactors that are used, both in catabolism and anabolism. There's a couple others on your sheet with like FADH2, FAD, and FMNH2, FMN, and so on and so forth. They can be 1 or 2 electron carriers. And again, we're going to use this both ways. Because technically, NAD plus goes to NADH as you oxidize your food. But then NADH gets re-oxidized back to NAD plus by the electron transport chain. And eventually, that's turned into a boatload of ATP.